Thanks. Thanks for the introduction. Thanks for coming back. So before we start, the plan for today will be to define this homology theory and cohomology theory for in tropical geometry. So definitions, examples, and there'll be a theorem in here too that will help us compute some examples without having to get our hands too dirty. But before we start, let's just recall where we ended last time. Was we introduced for a rational polyhedral fan. We defined for every cone some vector, some Z module. So this was in Rn. And we defined a system of these Z modules by looking at the pth wedges of the tangent spaces, the integral parts of the tangent spaces of all cones that are containing tau. Okay? So we went a little bit quick last time, but let's just do a simple example of our line case. So if this is a tau, we can look at what F1 of tau is, and we'll see that, okay, well, we're allowed to take one vector from any of the rays that are attached to tau, and this will be generated by minus E1, minus E2, and E1 plus E2. Okay, so we have three generators coming from the three faces, but of course there's a relation here, and it ends up being just the entire second exterior power of Z2. Okay, if we take a larger phase, okay, the system of generators here that we're allowed to take just comes from the face itself, which is a subset of the generators that we could take here. So. Oh, sorry, it's first. Thank you. Thank you. Okay, so here we only get minus E1 is the only generator. But just as a fact that the cones of a larger face will be a subset of the cones of the smaller face that are containing it, we get an inclusion map. Okay, so we always have this inclusion map when maybe I shouldn't use sigma here. Let's use just gamma or something. Not to confuse it with the generators. When tau is a face of gamma. Okay? So we also noticed last time, so just to continue the recall, that when we had sigma as being a matroid fan, we saw that these vector spaces, at least at the origin of the fan, recovered the cohomology of our complement of hyperplane arrangement, of our linear space, the part that lived in the torus. Okay, so here we saw last time that we got this picture from tropicalizing a line. I drew the real part of the line, but the complex points on that line that lived in C star squared, it would be a CP1 but with 3 punctures. Okay. So if we think about the first homology group of this P1 minus 3 points, okay, it's actually rank 2. So it's torsion free, okay, and it's rank 2. So here I'm using homology. This was isomorphic to Z2, which is, okay, I wrote this here because I made the typo, but we could just write this. Okay, so there's our theorem a little bit in action, at least from the point of view of the homology. Okay. So what we have when we've defined these kind of system of Z modules is we actually have a functor. So from sigma, thinking about sigma as being not just a collection of cones, but there's relations among the cones, inclusion relations. Okay? So I have a map. Every cone of sigma, I can associate to it a Z module. And if I have an inclusion of cones, I get a reverse inclusion of the Z modules. So let me write an op here. Okay. And I should write a sigma here. And recall we define these to be the dual of these Z modules. So we get a functor from sigma to Z modules where now the arrows, the inclusions in the fan are in the same direction as the inclusions that we get. Or not inclusions, actually, but the maps, dualizing these inclusions. So these are functors. And in other words, these are, well, I should write, this is a cellular sheaf. Co-sheaf, sorry. This one's a co-sheaf, and this one is a cellular sheaf. So here I use the Z coefficients. I could also change, just tensor with Q, use rational or use real coefficients. These will all pop up later in the lectures, but the kind of most basic one when we have a rational fan is that we can take integral coefficients. We could also quotient Z, coefficients. Okay. So these are particular instances of, yeah, question?
Maybe as a quick sanity check, do these actually depend on the fan being embedded in one vector space, or would this also work for like a complex of cones where every cone lives in a separate?
With this recipe that I'm giving you, it's highly, highly, highly dependent on the embedding.
Okay.
So here's an example. We saw this pop up as a problematic example when we tropicalized two different curves but got the same image. So this in R2 is combinatorially the same as this in R3, okay, where here there's one linear dependency, and here there are two. Okay, so you can check that if you look at F1 at this vertex versus F1 at this vertex, you don't get the same vector space.
The tangent spaces are all considered as living in one.
Yes, so this is really, you're using really the fact that the tangent spaces are all living in here.
Thank you.
Okay. Of course, if you want to just abstractly define a cellular co-sheaf or sheaf, you get to make up the rules. So this is one rule that I've given you. But whenever we have such a functor, or such a functor, then, yeah.
Just looking in there as a sanity check, if you take this the toric variety as this fan, so that's the homology. Is this well defined for the toric variety? Is this invariant?
So I haven't defined anything yet beyond these vectors, beyond these Z modules. Okay. Maybe one thing that I should say. The system is obviously highly dependent on the fans because I get an assignment from each cone. Right? So if I look at the collection of all of them, they know the fan, or they know the combinatorics of the fan. But if we look at the Z module at the vertex of the fan, which is what we did last time to see a relation with the Orlock-Solomon algebra, this actually doesn't depend on the fan structure. This depends only on the support. That's the kind of exercise to prove. So that if you kind of refine your fan, you can kind of see that you might get more generators, but there's of course going to be dependencies between them. Yeah. So this is So we will eventually make a link to the cohomology of toric varieties, but it's going to take a bit more than this. Okay. All right. So whenever we have, say, co-sheaf, so cellular co-sheaf, or say some cellular sheaf, we can define some homology and then cohomology groups by just using these assignments and some orientation maps. So let's define chain groups.
Your letters are H and?
This is a G and this was an H. Thanks. My math cow is not so good on the board. So I use a lower index for G because I'm going to use homology here. And I'm going to put some decoration in a second. But what we'll take is a direct sum over all Q dimensional faces. Let me write dim Q. And I'll add some condition here in a second. So this is the definition of this cellular chain group, the Q chains. And because we have these maps I, we can get a kind of a differential map. Let me just write the differential map and then I'll explain what it is. To the Q minus 1 chain group. So this is again a direct sum of these, but now with lower dimensional faces. Okay, so for each one of these, each one of these G sigmas, there's going to be a map to a G tau if it's a face of sigma. Okay, so normally when we take cellular homology, we have an orientation of all of our cells. We define the differential just using those orientations. Now we have to define our differential using the orientations and the map I that would go from every sigma to every tau. So this differential is like an I. Let me just write it like this, composed with the orientation maps. Okay? And then analogously, we can define for a sheaf the Q cochains of the sheaf as, again, just direct sum. And then we have a differential going in the other direction. So now our differential goes up. Okay, so we have Q dimensional faces. And I'll put a little decoration here and a decoration here. Okay? And then as you can guess, to get the homology here and the cohomology, we'll just do the usual thing once we get these chain complexes. These are chain complexes.
Sorry, what do you mean by the rectangle?
I can't hear you.
Rectangle.
Yeah, I haven't said yet.
Okay.
I haven't said yet. Okay? So right now I've said I've taken all Q-dimensional faces. If you know in cellular homology, when you have some unbounded faces, okay, you wouldn't add those into this sum. So here's your, you can take this cellular subdivision of R. All right? And we shouldn't take these two unbounded faces if we want to compute the cellular homology of R. So if we want to have this empty, if we leave that blank so that we're doing usual then we restrict to bounded cells. or compact cells. So we would put in here compacts. And if we put in this box in the uppercase BM for chains, or C as in compactly supported for cochains, then we restrict to, we use all cells. Okay? Does this make sense? So this BM is for Borel-Moore, and this C is for compactly supported. If you know what those means and you've seen them before, then you can think to yourself why that's the right thing to do in the cellular case. If not, take it as just a definition for now. Yeah?
Maybe I'm getting confused. If you say a bounded cell, so I'm thinking of a cell as an element in the...
Of the fan. So cone in this case.
So, okay, so you're thinking of like height 1 points? When you say a bounded
Okay.
cone?
I'm sorry. I meant to change this to actually any polyhedral complex, and that'll make this more interesting.
Okay.
Thanks. So here we've defined these for fans. But if we have any polyhedral complex, okay, we could also have functors from the face lattice to, say, Z modules. Okay. And now there could be some more interesting.
Okay. So in the case of fans, you just want there are no bounded cells except the trivial ones.
Yes, thank you.
Okay.
That's going to be a point later. But sorry, I meant to make this switch from here to here. Good. Okay. And we had these functors defined for fans, but we could also just copy that definition for any polyhedral complex. All right, so these we can also, if we have a polyhedral complex in some big Rn, we can extend these assignments to any face, because we just use the tangent space and the lattice in each tangent space. And so we can form these chain groups, either the Borel-Moore versions or the compactly supported versions, and we can compute their homology and cohomology.
So when P is a fan, then the only bounded cell is
Good.
the original point, then when square is empty, then the constant chain true.
Yeah. Right, then we only have, if we leave this empty, then we only have and then we can even very easily compute the cellular homology of this thing. The cellular homology will just be, for q equals 0, the sections at the origin, so this thing, and otherwise it's 0. Okay? And we could also write down the analogous thing for this mathcal H sheaf. So that's easy. But otherwise, we get something interesting. Even for a fan, if I put Borel-Moore here, you can ask yourself, what on earth do we get? Okay. So we can do that example over here. So remember, this was rank 1 for every edge, and this was rank 2 at the vertex. So if we look at this chain complex with a BM here now, something a little bit more interesting, then we get, well, 0 in degree 2. Degree 1, I have 3 edges, so I take F1 here, plus F1 here, plus F1 here. So that ends up being isomorphic to Z to the 3. And at this point in the origin, we just have, this is F1 at the origin. So what does this differential map do? If I take an element in F1 along this edge, that's taking a vector parallel, integer vector parallel here. And then when I take the differential of something that is in here, I'm going to sum up those vectors, the one I get for each edge. I'm going to sum them up and see what I get. And when do I get 0? Well, if I take 1, 1 here, minus 1, 0 here, 0, minus 1, we know that this thing is balanced, and I get 0. So the kernel here is rank 1, and it's generated by this balancing that we had. So H1 BM of this F1 was isomorphic to Z. And we even can think of this, we'll see that we can think of this as a fundamental class. And it's not too hard to see what's then remaining. What do I get then H0? Well, I get 0. This map is surjective. So if I even just take this edge and the vector parallel to it, mapping, it gives me E1, and this edge will give me E2. So this map is surjective. Okay. And what we'll see next time is the nice fact that this is, in a sense, dual to, so this is for next time. It's not a coincidence that this was rank 1. This is actually the same thing as H0 of F0 star. So we'll see a form of Poincare duality, or maybe better to call it Verdier duality, for certain tropical spaces. This won't work all the time. Okay, so let's get just some shorthand notation. We did our first computation. It wasn't so bad. Well, we did this one too. Sorry, say it again. What is F0 and F1? If you want, so maybe by default, we just say that this is always Z for any phase. Okay, so F0, we should think of F0 as being the kind of constant Cauchy Z. Okay.
It's for P equals 1, right?
Say that again?
The sequence you wrote is the chain complex for P equals 1.
Yeah. This is a chain complex F1, so P equals 1. Thanks. So here's a definition, but there's a statement contained in this definition. So let's let X be the support of some polyhedral complex, and I'll have to say that P is sufficiently, let's say, fine. So if you're familiar with what happens when you want to prove an equivalence of, say, cellular and singular homology, you need your cellular complex to be nice enough. So usually the one-point compactification should be a regular CW complex, something like that. Okay, so we will need to be a little bit careful. So the tropical homology groups of X are, I'm going to define homology and cohomology. So if we put a PQ down here, yeah.
As someone's computation, this also groups should live in lambda 1 z squared.
Yeah, so these were isomorphisms, if you want. Yeah. Lambda 1 z squared is just z squared.
Yeah, how can you have
Ah, no, this is a direct sum over all of the formula here tells me for each edge, I take the direct sum of this. So each one of these is in Z2, but the direct sum of them is not.
That's what's really inside the block, but that's
Oh, sorry. Okay. And again, a little box here, because maybe we want Borel more or not. That this is the Qth homology of this chain complex with the same box here. So, and the cohomology, again, with a box here that may have C contained in it for compact support or not. And, again, this is the cohomology of this cochain complex. Sorry. The box goes here. Okay. So there's a statement in here that there's some sort of independence of the choice of P, right? Because I've defined something for X, which just has the support of some polyhedral complex. If I take another polyhedral complex, say refinement, why should these be the same? So but that is a fact. So I just included that fact in the definition. So it's independent of the choice of P. Which even in the fan case, this is not obvious. Okay. All right. So there's the definition, and this definition is actually due to Eatonberg, Katsarkov, McKelkin, and Zarkov. And you might ask yourself so far, why is it there's nothing at all tropical in here? Right? So I just took a polyhedral complex to get Z coefficients. And I should be aware that since I will change coefficients if I have to, I'll put the coefficients with a comma, the ring. Okay, so right now take this as being integral coefficients. But we will soon switch it up to be rational so that we can actually say something about why this is an interesting definition. So if you want, you can. So when this is going to be, let's say, unbounded. You would want something like the 1-point compactification of this thing is a regular CW complex. So for example, this, if I take R of just one open cell, when I take the 1-point compactification, that's not a regular CW complex. So this is, though, in fact. Okay? So if your P is not good, subdivide enough and it will be okay. Okay? So this is a theorem of Eatonberg, Katsarkov, McKelkin, and Zarkov, and I think it's from around 2016, but it was around a long time before that. Yeah.
Just another quick sanity check. You didn't define the FPs for polyhedral complexes, right?
But I said that there's no difference between the definition in the fan and the polyhedral complex case. So remember, we used just the tangent spaces of neighboring faces to define it for a fan. You can do the same definition for a polyhedral complex.
Okay.
Okay?
Maybe a follow-up question, that's okay. You probably don't get the usual homology if you take like a triangulation of the sphere and as a polyhedral complex and plug it into this?
If you take P equals 0, you should.
Okay.
Yeah. So P equals 0 should pretty much recover just usual Z coefficient cellular homology.
Okay. Thank you.
Because we have this.
Oh yeah, then you just have like cellular.
Then you just have cellular homology.
Okay.
Yeah.
Okay.
What you mean is independent of choice of P?
So you could take another polyhedral complex that has the same support, as long as it satisfies this condition. You'll get different chain complexes, but when you take their homology or cohomology, you get the same You get isomorphisms. Okay. So this theorem relates these invariants to, well, Hodge numbers and even mixed Hodge structures. So let's let pi be a projection map from a family of projective varieties to the punctured disk. Over the punctured disk. We can tropicalize such a thing. So now we're not tropicalizing just one variety, but we have a whole family. So this is sort of akin to what Alex had talked about in his lectures. We can also think that maybe these are defined over the field of Puiseux series, so there's some coefficients in their defining equations. Okay? But we're not asking for it to be a family over all of A1. This is a bit looser. If you want, think of it as a family over A1, but you can get more general things from this setup. If the tropicalization of this family, so this will be some set somewhere. So these are projective varieties. I haven't told you yet how to tropicalize projective varieties, but we can do that. If this is locally matroidal, so that means that every neighborhood, if I kind of look at the thing, if it's got the support of a polyhedral complex, so I can kind of look at the support around a face, the star around a face, and if that is the support of some matroid fan, I call it locally matroidal. Then the dimension, let's call this x, just to gel with that. The dimension of HPQ of x with q coefficients, because I wrote dimension now, is equal to little HPQ of xt, where xt is a generic member of this family. Okay, and these are Hodge numbers. So this is a numerical statement. Yeah?
The varieties to be smooth.
Yes, thank you. Yes. So I want to have a nice pure Hodge structure on these things. Thank you. Yeah. So this is just a numerical statement, and actually their theorem is far deeper. It's actually relating what these groups are in terms of the mixed Hodge structure of the family. So these are actually isomorphic to the graded pieces of the weight filtration of the so-called mixed Hodge structure of the whole family. Okay? No. No. So except in certain cases. So we're gonna do the hypersurface case in a second. Yeah.
Is there any constraint on the type of foundation? Should it be semi-stable or it's also nicely?
Yeah. So you would you would want to have a semi-stable completion. You want to. I mean, the thing is that what these basically are computing is something about the special fiber. Right? And then, I mean, the fact that in your degeneration, everything is locally matroidal actually translates algebraically to meaning that the open strata are these complements of hyperplane arrangements. And those are all nice, pure mixed Hodge structures. And that's what lets us deduce this. So the proof here is basically using a spectral sequence to, and seeing that, well, you can do some yoga with spectral sequences and get something that the Illusi spectral sequence is kind of matches up on a page with what you get when you have a spectral sequence for the tropical homology. So the thing that's, I think, really deep here is actually the theorem that we saw last time. Or not deep, but the thing that's combinatorial, let's say. Because you can play the spectral sequence game with the Illusi spectral sequence in other settings as well. But what this locally matroidal thing is giving you is that you can compute stuff just combinatorially, just purely from the tropical image. Normally, you would need to know the cohomology of each strata in the special fiber. But here it's saying you know it if you know the tropicalization. But we know a lot of things about Hodge numbers. So if we're just interested in what are the structures of these, these homology groups, what are their ranks? Do they have torsion? I mean, this doesn't tell us anything about torsion. At least here we already know that in this setting, we can say, at least dimension-wise, at least numerically, that we have some relationships between HPQ and, say, QP. Yeah? I haven't used that word, but yes. Yeah.
Here, tropicalization with respect to C double bracket T.
If you want, if you've defined your thing over C double bracket T, if you've defined over the field of Puiseux series, this is allowing you to be a little bit more general and having analytic families. But, okay. So for example, we would get, if these are the tropical groups, we have their dimensions are equal, so we have some symmetry. We also have, if this is dimension D, we have a Poincaré duality statement for the Hodge structures that would give us this relationship. We also have Hard-Lefschetz property on this xt, which gives us a system of inequalities between these numbers. And we also, well, not on the graded pieces of the weight filtration, but on the pieces of the Hodge decomposition, we also have like Hodge-Riemann bilinear relations and all kinds of properties here. And sort of, well, one industry, at least in the realm of matroids, has been generalizing all those properties to the Chow rings of matroids. We'll see a link between this tropical homology and Chow rings next time. But we can also ask for just more general varieties that don't tropical varieties that don't arise as this tropicalization, that don't fall into the realm of this theorem. What are the numbers that we're getting out? And can these be useful to study combinatorics? So there's one little thing here that I said, we didn't talk about tropicalizing projective varieties. We talked about tropicalizing things in the torus. There is Sam's Paint's extended tropicalization that you can look at. We'll get into this more next time, but essentially, if you have a toric variety like projective space, you have a bunch of open torus orbits. You can tropicalize in each one of those, but then you should kind of glue them up together. And that's what this extended tropicalization can give you. Yeah?
What is an example of such a parameter?
So we'll get to hypersurfaces in a bit.
Sorry, locally around this face looks like a Bergman fan.
Looks like the support of a matroid fan.
Support of a
Yeah.
Bergman fan, you mean Bergman fan?
Yeah, or the, Bergman fan of a matroid. Or I called it the Ardila Clivens fan.
It's a strong condition, yeah?
It's a very strong condition. Yeah, it's a very strong condition. And in most cases in practice, we don't know how to verify this. Okay.
Sorry, but then this tropicalization depends on the embedding in the project.
Of course, absolutely.
But the theorem is true for any such embedding, such that.
No, because the tropicalization is also sensitive to the embedding. So whether this is locally matroidal depends on the embedding.
Okay.
Yeah?
For any.
So I removed this picture of this and this. This one in R2 and this one in R3, with a different embedding of the same curve, you could actually produce this picture. We don't know how to kind of resolve these. There's no sort of tropical resolution of singularities yet either. So we don't know if there's always a way of embedding your family of projective varieties into, say, a larger projective space so that when you tropicalize, you do get something that's matroidal. I also want to say that we define these groups with cellular homology and cohomology. There's alternate definitions. This is not a complete list. But we could use singular chains or cochains. And they have to respect the stratification given by P, and then you get coefficients given by FP still. And another one, let's say, we could also make these, say, FP into a sheaf in the Euclidean topology. So right now it's a cellular sheaf, which is actually a sheaf in the Alexandra topology. Another one that I think is interesting in terms of Hodge theory is we can define superforms. So these are actually real valued differential forms that have a fake bigrading. They have a kind of D prime and a D prime prime. So they're P D primes and Q D prime primes. And you just fake it till you make it, basically. You can define a differential that goes up in Q, so like a D prime prime. And you get complexes of superforms, and we proved the de Rham theorem, which says that when you resolve these, you basically get your FPs out. Okay? So these are Lagerberg superforms. And with Yell and Smaka, we proved a kind of de Rham-like theorem that the cohomology of these superforms actually gives you tropical cohomology. And what's nice about these superforms is that they'll lift to Berkovich spaces. So if you have some superforms on the tropicalization, Chambard, Loire, and Ducrot pulled these back to get bigraded differential forms on Berkovich spaces from tropical charts, essentially. Although computing what the cohomology of superforms are on Berkovich spaces, I think this is an extremely difficult task.
Sorry, the content of theorem, I didn't understand something. Why do you need a family?
Because it makes it more interesting. If you want to get something that's locally matroidal and you don't have a family, you're going to start with an L that we started with last time. You're going to start with a linear space. This is a theorem of Alex's, basically, recoded. Okay? So having a family means you'll get more interesting polyhedral complexes. So I want to look at the example of hypersurfaces and link to actually one of your questions yesterday, Q. So a hypersurface, a tropical hypersurface, this will be X and Rn, say of codimension 1. And these actually are always in the situation of the theorem, they always arise as tropicalizations. So this is a support of a polyhedral complex with a weight function satisfying balancing condition. So there always exists a family of hypersurfaces such that the tropicalization is equal to this X. And this locally matroidal condition comes down to, so there's always a dual subdivision. Thank you. It's dual to a subdivision of the Newton polytope. Okay? And if it's a unimodular subdivision, then it's if and only if we have this matroidal condition. So here we're in the situation of this theorem. So we know all of the tropical Betti numbers with Q coefficients as long as we know the Hodge numbers. And here, not yet. let's take X bar, the projective compactification. The extended tropicalization. Say, compactify this to a complex projective space. Okay, so then we know all of these Hodge numbers. We know that all the dimensions are equal to Hodge numbers. And Danilov-Khovansky gave us a formula for HPQ of X bar, and even more generally for coming up with the chi-y polynomials of just X before I compactify. And all of this is already combinatorial. Okay, so the numerical statement is not really doing anything for us more than Danilov-Khovansky, but this is kind of a categorification of Danilov-Khovansky. It's saying we can get these numbers by computing cohomology of chain complexes. Yeah?
Why can you embed your family into EN?
Um,
You want that everyone is projective, but why can you do it simultaneously?
So in this case, I didn't say how I got my X. My X will be given by a family of polynomials. And actually, I want them all to have, I want this Newton polytope to be a standard simplex. Okay? So they'll all be in the kind of same linear system, and the tropicalization of it will also compactify nicely in some tropical projective space. Okay? So this is a case where we kind of already knew the numbers many years ago, but we're cooking them up again. What's kind of interesting is that we also had these Z versions. And it turns out that the HPQ of this X bar, let me put a Z here, just to remind us that we're using the Z coefficients. These are torsion-free. So this was not easy to prove. It was actually a total pain to prove, but we did it for reasons of an application. And the reason why we wanted to prove that these were torsion-free was because this gave us an application to patchworking in real algebraic geometry. This allowed us to bound Betti numbers of real algebraic varieties, let's say near the tropical limit, in terms of Hodge numbers. So these bounds definitely don't hold for all real algebraic varieties, but we showed that they did in this setting. And one last thing, so this subdivision here is regular. In this case, we come from a variety, tropicalize it, and we get the subdivision. It's a regular or convex subdivision. And then we could say that all of these properties of Hodge numbers are coming from the geometry of X and the Hodge structure of X bar. What is very strange but combinatorial is that if delta is a subdivision is not convex, so there's no tropical hypersurface X involved, but we can still define on this subdivision something like tropical homology. The dual subdivision has the same face poset, but just reversed as the tropical hypersurface. So instead of putting your FPs on the tropical hypersurface, put your FPs on the polytope.
Convex with regular? Or
Yes, sorry. So you can still define something akin to the tropical homology. So if it has a regular one, you would get the same homology groups as you did with X bar. And it turns out that all of these theorems still hold. You still get Hodge numbers, even though there's no geometry laying around. You still get that their integral versions are torsion-free. And you still get this bound, except it's not real algebraic varieties. It's some kind of patchworking that's beyond the algebraic case. So all statements are still true, that we know that the Betti numbers are Hodge numbers. And this was proved by Brugale, Lopez de Medrano, and Johannes Rau. And so this is another instance where there's no reason from geometry, from complex projective geometry, that such a statement should be true, that Hodge numbers should pop up in such things. But you do some combinatorial work and some proof, and it falls out. So this is something that's very familiar for those who know the Matroid game and Chow rings of Matroids. Just want to put one more statement on the board to link with Alex's talk, if that's okay. Oh no, I'm already over time. I wanted to say that we can also show that the tropical homology of the linear spaces that Alex introduced in his talk ends up being the exact same as Matroid fans. So there's sort of, but this has a nice combinatorial interpretation as a kind of categorification of the valuative invariance that Alex introduced. Okay, I'll stop there. Next time we'll come up with tropical compactifications of fans and relate to Hodge, relate these tropical Hodge numbers to Chow groups of fans.